this. The theme of my presentation is the importance of refined resolution near the coast in global models. We're moving into a world in which their climate models are starting to resolve processes. We were talking before the seminar with Craig and I, and a lot of the models are actually moving to the point where we're starting to resolve much better the coast at the quarter degree or even the higher resolution models. And we're running these for climate, maybe not routinely, but we're starting to look at simulations. And I'd like to give you some reasons why it's pretty important for us to continue pushing that resolution bound in order to understand what may actually happen regionally and coastally with sea level. So by the way, this is a picture I took 3 years ago. As a modeler as well as a theorist, I also go to sea. Hopefully I'll go back again. I was in the Southern Ocean 3 years ago doing some work with the British in the Orkney Passage region, looking at bottom mixing. I won't talk about any of that today though. So resolution, I like to give this slide when I give a sort of overview talk of resolution. On the left, you see Dolly's vision of Lincoln. On the right, you see a photograph. So when I first came in the field 25 years ago, a lot of the models could arguably be called Dolly vision versions of the planet. And we're hopefully moving more toward a clear vision or a more photographic vision. As much as I love Dolly, I would prefer to run simulations when we are interested in accuracy, simulations that more represent the right picture here of Lincoln. So resolution, there's a few different ways to define or to measure resolution. The top figure here is a figure from a paper by my colleague in Princeton, Bob Hallberg, in which he plots the grid scale required to resolve the Barracklinic-Rossby radius, the first Barracklinic-Rossby radius, using two grid points per radius. And as you see, as you go to the higher resolution, you get to very fine resolution requirements. And the mid latitudes and low latitudes, you get more coarse resolved features. So this puts a strong constraint on what we can think of as resolving mesoscale features, and then even beyond that, the submesoscale. So we're going to be well beyond my retirement age before we can get global climate models getting to the 1 or 2 kilometer resolution that we need for the high latitudes here. But nonetheless, we can get a lot of features that are well represented, if not perfectly represented, as we go to fine resolution. In addition to the mesoscale, the ocean is strongly driven by the topography, the land-sea boundaries, and the bottom itself. And as you increase resolution, even incrementally, you do substantially better as you go to finer resolution with that representation of the bottom of the ocean, and in particular the shelves. So the bottom picture here comes from David Marshall after Peter Kilworth, and it just gives you a symbolic realization of the different scales that we have insofar as numerics relative to the atmosphere. If the atmosphere resolved their grid analogously according to the mesoscale, according to the ocean, then you'd have 30-degree latitude grid boxes in the atmosphere. So a 1-degree model in the ocean is roughly corresponding to a 30-degree atmosphere model if you use the first Barracklinic-Rossby radius as your measure. So it's a difficult problem computationally to get mesoscale eddy resolving models, but nonetheless, my contention is going there incrementally as best we can at each computational upgrade improves our representation of the ocean in ways that are important. So one of the models that we have built in the last decade at GFDL is a hierarchy of ocean models that are coupled to climate models. So they're coupled models. We call it the CM2-O suite of models. And we've written about 40 papers making use of this hierarchy of models. It runs from 1 degree, quarter degree, and 10th degree resolution in the ocean. Everything else identical. Atmosphere identical, ocean, ice identical, land identical. The only change is the ocean resolution. And we get a huge amount of interesting understanding of the importance of the mesoscale when we look at simulations from this suite of models. On the top left figure, you see a VSO, sea level variability or standard deviation. The top right is the 1 degree, then the quarter degree, the lower left, and the 1/10 degree lower right. And you see as you go to finer resolution, you start to do better. This is not something new. People have been showing this for 15, 20 years now. But what we did show in this suite of simulations in particular is the importance of the heat uptake and the mesoscale eddies in affecting the heat uptake. In the lower panels here, you see three different figures here, 3 different panels. The left, middle, and right And what you have is the horizontally averaged temperature as a time series deviation from the first year of the simulation. So we have about 140-year simulations for all three models. And the lower right is the 1 degree, and the lower middle is the 1/3 degree, and the right is the 10th degree. And you see a very different amount of heat uptake according to the resolution of the models. And we did a bunch of diagnostics and analysis of the simulations, and the smoking gun reason for the differences is that the stronger mesoscale eddy features in the 1/10 degree have a big effect on the vertical transport of heat. That you don't get that much eddy effect in the 1/4 degree, it's poorly resolved, and so you get a weaker eddy effect. In the 1 degree, you have parameterized eddies that are partially parameterized, and so you have something sort of in between the 1/10 degree and the 1/4 degree. So the story, the take-home point from this figure is that resolution of eddies has an important effect on climate, in particular heat uptake, and heat uptake insofar as it affects thermospheric sea level is important as well. And so some of the cutting edge research questions for eddy parameterization is trying to get better representation of the mesoscale that corresponds more to the 1/10 degree simulation here, and so that you can get a 1 degree class of model that looks more close to the 1/10 degree. The 1/4 degree is kind of a gray land, a gray zone that a lot of people don't like. They like to jump over that zone. But as I'll show in this talk, I'll show some resolutions of a 1/4 degree, which are interesting because of the resolution of the topography. So I'm going to move through 3 or 4 different case studies of work that we've done with this hierarchy and moving into some new models that we've developed at GFDL for CMIP6. So the first case study is a Northwest Atlantic, and it's not necessarily a sea level story in this case study. It's more of a sea surface temperature and bottom temperature story. But insofar as temperature affects thermospheric sea level, it is important for sea level along the coast. And this is based on a study from Vince Saba et al. That came out 4 years ago, where we were looking at the Northwest Atlantic and in particular the Gulf of Maine and the response to the AMOC reduction in the simulations. So the Gulf of Maine that you may not realize is actually the planet's most severe heat hotspot for ocean heat waves, people call it. The Gulf of Maine is warming more than any other place on the planet, if not, maybe more is not quite right. It's among the top heat hotspots on the planet, and it affects the biology quite a lot. So the biological people, the ecosystems people, are really interested in this region for a lot of reasons. And Vince Saba is actually a biologist that works at a fisheries person that works at GFDL. So in the model resolution hierarchy, let's look at that part of the planet. Let's look at the Gulf or the North Atlantic. You have the 1/10, the 1/4, and the 1 degree shown here, and the outline in black of the boundaries. And the 1/10 degree, you could really think of that as just a realistic map. The 1/4 degree, it's starting to get a little bit coarser, and the 1 degree, you're starting to see that the embayments and the different features on the coast are not resolved at all. So what happens in these models when you weaken the AMOC? And this is an old story as well. And this is a picture from a paper from Cesar et al. With Vince Saba as a co-author, where they were looking at SST fingerprints of AMOC reduction. In the left panel is the model, and the right panel is the Hadai SST. So what you typically get in the North Atlantic is a cooling in the subpolar region and a warming near the West Atlantic, near the coast of North America. And you see both of those patterns in the model and in the SST from Hadai ST in this model. So let's blow up a little bit more close and focus on the Western Atlantic and look here in the model. And I apologize for this poor color choices here, but this is, old-fashioned colors. If you were looking at new color palettes today, you would probably cringe at this figure. What you're showing here is the Northwest Atlantic, and in particular what's called the Northeast Channel near the coast of the Gulf of Maine. And you have the and the color is the topography. Okay, and in the insert you see a temperature salinity diagram. The top left is observed. Then you have the 1 degree, the 1/4 degree, and the 10th degree model representation of the water masses in that region of the ocean. And as you can see, this is kind of a verification or validation of the model to show you that the 10th degree model does better in this realization of the ocean with the with the water masses in that region than the 1 degree or the 1/4 degree. So that's good. So we can trust at least this model that it's not doing something that's completely different planet. So let's see what this model does when we warm it and reduce the AMOC. So the finest resolution model, the 10th degree model, which resolves these channels and these embayments, gets a tremendous warming up to 5 or 6 degrees in those regions where the other models don't get much at all. And as I said earlier, observed warming in this region is getting upwards of a few degrees. And so the idea that over the course of this century, we're going to get to 5 or 6 degree warming in the Gulf of Maine is very, very much of a concern for the fisheries people. And so the fisheries people have taken this simulation and done extensive amounts of studies, both off the east coast of the US and the west coast and around the world with ocean heat waves and the impact on fisheries. So let's get some summary points from this particular case study. So the refined coastal resolution enhances the simulation of coastal water and their properties in regions around the Gulf of Maine, and which is key in North Atlantic for fisheries, and as well as other regions of North America. In the idealized double CO2 simulation that I showed, the warming in the Gulf of Maine is really big in the high resolution model, and that is correlated directly with reduction of the AMOC, the Atlantic meridional overturning circulation, in this simulation. The SST fingerprints from this model show intriguing similarity to SST trends of observed, and the Cesar et al. Paper tries to make the case that that's a fingerprint of AMOC reduction. I'm not going to go into that argument here because I know there's lots of debate in regards to whether we are actually observing AMOC reduction or not. Cesar et al. Have an argument that we are, others say that we're not. The core simulations in this particular region do not show much warming. They do not resolve the coastal currents, the topography, and the coastal warming of those climate change simulations. The temperature results translate into sea level changes near the coast, and I'm going to show some of that later. So of course, as you warm the coast, you also rise sea level, as well as change the Gulf Stream, you rise sea level. So the next case study, let's look at, this is not really a paper, but this is just a comment on the capabilities to represent the sea level on the west coast of the US and the representation of those sea level changes from El Nino. So same figure, west coast of the US, looking at the different resolutions of the grid. This is a smaller domain, so you start to see the black outline even at the 10th degree on the left. The middle is the 1/4 degree, and the 1 degree is on the right. One thing to note about the coast along the west coast of the North America is that the continental shelf is much more narrow. And so to resolve the coastal processes, namely the waves that happen along the coast, you need even a finer resolution than you do on the east coast of the US. So this picture here shows a regression analysis between El Nino and sea level. Actually, it's a sea level pattern for El Nino, which is not a regression, but a peak monthly maximum in the models, as well as in the observations. The top left, the ENSO observations, you see the big picture is the typical sea level pattern from El Nino. But if you zoom in to the west coast of the US, you see a rise along the west coast, Washington, Oregon, California, Baja California. Now, what do we do in the models? In the right panel, you see 3 different depictions of that same behavior in the models. And you see, somewhat better or worse patterns for the big pattern of El Nino. But if you blow up and look toward the coast along the right, which is covered because I can't see y'all because everybody is covering it, but hopefully you can see it, you start to see more and more representation of that coastal rise as you go to the 10th degree resolution. And it's not even as much as in the ENSO observational analysis, but nonetheless at the 1 degree, you don't see much at all. So if you were going to ask questions about coastal sea level changes in a 1 degree climate model, or even fluctuations of coastal sea level due to El Nino, you would be in a very hard to do that in a 1 degree. Even a 1/4 degree model would be difficult to do that. You need to get to the final resolution where you start to resolve the shelf in those models. So it's a caveat. I don't know how you would parameterize that. It's just a limitation of the models, and it's something that you need to be acknowledging when you do that. You might try to do a downscaling from a 1 degree model to maybe a 1 kilometer shallow water model or something to that effect. And I'll have a comment about that in a slide or two. Actually, I'll have a comment about that right here. So the summary points from this little case study is to represent the impacts of large scale climate fluctuations on sea level requires grid resolution sufficient to resolve the shelves, which is similar to the statement that I made in the Atlantic case study. Also, it's something to keep in mind. I'm not going to talk about this here, but the time scale and the amplitude for coastal signals are largely driven by waves. The mesoscales that I started talking about in the earlier part of this seminar really don't hit the coastal shelf. They get bounced back, and there's a wave sort of filter. Most of the coastal signal in the shallow continental shelves are waves, and they can be sensitive to the resolution. There's a review paper that Chris Hughes led just a year or two ago, in which we talked about the coastal signals and their relevance to sea level. It's common to downscale, and we heard some nice talks. I can't remember when. It was a month or two ago in this seminar series about downscaling from a colleague of mine in Princeton, now I think at a university in New York, looking at hydrodynamic models to downscale. And I think that they're going to be forever required, because they get to resolutions that are going to be so far beyond the climate scale that it's going to be many, many decades, if not the century, before we can get routinely simulating models that resolve, say, a 10 or 20 meter resolution that some of these models can do. Having said that, I think it's important to acknowledge the limitations of those models. The technical issues are pretty profound, related to how you force these models at their boundaries. And it's important also to acknowledge that they don't capture feedbacks and interactions that the coastal circulation feels from large-scale climate modes when you're running these climate simulations out to future projections. And the main point here is that the world is more complex than the trend plus noise assumption that you need to make when you do these extrapolations with these downscaling models. Also, from a conceptual perspective, I think it's important to realize that you kind of lose a connection between the mechanisms of what's causing sea level changes when you decouple those changes and you just do a downscaling problem. So I think there's important understanding that still needs to be come from how the ENSO and the NAO and the AMOC and the tropical cyclones affect sea level, and how sea level can feed back on those modes as well. So a big part of my research in the last few years is focused on the Southern Ocean and the Antarctic. Part of the motivation for that is looking at the Antarctic continental shelves. And I remember talking to Craig at the beginning that I even left off one or two studies that I've also been part of that are not on this list, but I can only show you so much. So the big question down there is the role of the ocean heating the underside of ice shelves. As I'll show, there's warm water at depth, the circumpolar deep water, that's kind of kept offshore from the coastal ice shelves. And there are ways in which that water can impact or impinge upon the underside of the ice shelves and affect some melt. So I'm going to go through a suite of talks here, starting from the CMIP3 era models from the Yin et al. And the Francombe et al. Studies, and then move into some finer resolution 10th degree simulations from Spence et al. And Goddard et al. So as motivation, there's a lot of melt going on around the Southern Ocean in the Antarctic shelves. This is a figure from a paper by Paolo et al., in which the red dots mean melt, and you see especially along the western side of Antarctica, there's lots of melt going on, ice shelf melt. So adjacent land ice melt represents a significant, when you melt the ice shelves, you can allow for more land ice to enter the ocean, and that can represent a significant and growing contributor to sea level rise. The relatively warm sub-ice shelf seawater is, in many places, the dominant contributor to ice shelf melt. And so we can raise some oceanographic and climate questions. What are the physical mechanisms that may affect some warming under the ice shelves? How does that water get there? And are there any of these mechanisms that are subject to change as climate changes? Say the winds change in the Southern Ocean, or you have more precip or melt down there. What can that affect some of these mechanisms? So let's start by looking at the era CMIP3 era models. And so you see kind of what you see is these ensemble mean of sea level changes in this region, and you see large scale patterns, little representation of the coastal processes in these models. And you see, actually this is changes in temperature. The coastal processes that are key to the under ice shelf interactions are completely missing in these models here. And nonetheless, they're provocative, and a lot of changes in the winds, as we see in this figure here from Francombe et al. Are largely Ekman-driven changes. Now, this is a sea level change. I switched from sea surface temperature to sea level changes. What's happening in the atmosphere down there is a lot of the atmospheric reanalysis shows that the Southern Ocean westerlies are shifting poleward, and the climate model projections see increases in this trend, particularly due to ozone, and the southern annular mode becomes more dominated by CO2. Antarctic regional wind patterns are also correlated with large-scale indices of El Nino. So there's key impacts on sea level rise from the southward shift. And there's actually an interesting result that is, again, not that new, but some of it's come out in some of this work here, that the shift in the winds, the polar shift in the winds gives you much more bang for your buck than the increase in the wind stress itself. Okay, so if you really want to change the sea level patterns in the Southern Ocean, you shift the winds instead of just increasing the wind stress. And a lot of these patterns that we're seeing here are largely Ekman driven. They lead to sea level drop near the coast and a rise toward the south. So you see the blue in the middle and the right panel is a sea level drop due to the Ekman changes. And the sea level rise is the red and in the middle of the Southern Ocean, Antarctic circumpolar current. So now let's get more toward the coast. So a key question here is what, when, and where warm offshore circumpolar deep water might move toward the Antarctic continental shelf and under the ice. This is a slice of an observed figure, a measured ocean temperature from a paper by Ron, 2017. And you see this relatively warm water, the red, and this is the temperature field, and the colder water near the shelf. And of course, the reason that the water is densely, stably stratified is because salinity is a dominant feature of the density stratification in this ocean, the Southern Ocean. So you can see cold over warm, and that's still stably stratified because of salinity effects. So again, I'd like to give a shout out to Ruth Mormon's talk, which I believe is recorded, and she did a lot of work on this problem using a model that's very similar to the model that I'm going to show today, and looking at some of the more refined features of how warm water gets to the coast. So this is a figure that I took from a proposal that I was peripherally related to, and it's a partially funded Australian Center of Excellence for Antarctic Science. And it depicts some of the interesting processes going on around the Southern Ocean and the continental slope and shelf that we need to be moving toward resolving in process models, and maybe eventually in the next decade in fully coupled climate simulations. So you see a tremendous role for air-sea interactions and ice-sea interactions and katabatic winds, and slope flows and dense overflow processes. And you see some biological processes because this project, this Antarctic Center, is also related to biological processes as well. So there's been in the literature the last 5 or 10 years, well, really probably the last five-ish, well, maybe close to 10 now years, some mechanisms for potentially warming, getting some of that warm offshore water toward the coast. So there's lots of role for tides, some people think, and these are some studies that go back to Robertson, 2013, Stewart, Clockerman, and Menlis, 2017, who've done some work on simulations and a very, very high resolution model that's like 1 kilometer resolution, but it's only been run for a year. So there's lots of limitations in the ability of that model to do some processes, but nonetheless, they have tides and they show some role for tides and moving warm water back and forth across the shelf. Another study, which is very intriguing, is the role of the mesoscale eddies themselves. And I said earlier, mesoscale eddies are typically have a barrier when they hit continental slopes, but you can have some penetration across the slopes of eddies in some regions. And Thompson et al. And Artun et al. And have looked at different regions where you can get eddies propagating across the shelf, and in particular where there's an isopycnal connection to the base of the ice shelf and eddies. You can get some transfer of heat across the shelf through isopycnal transport. And actually there's a paper that I was part of that I'm not going to talk about too much by Bronsler et al., in which in a coarse resolution climate model, we see that mechanism, the eddy effect along isopycnals, can be an important mechanism for moving warmth from the deeper ocean toward the continental shelf. Now, another mechanism which I was part of looking at in a study that I'll show in a minute relates to what's called arrested Ekman layer dynamics. And that's for the GFD cognoscenti in this audience, a very interesting way of looking at Ekman layers on sloping bottoms. And you can get, in certain geometries, you can get, even with linear waves moving around the coast, you can get an Ekman layer, an arrested Ekman layer response, which brings warm water up towards the ice shelf base. And I'll try to outline that in a couple of slides. One of the other changes is just due to the wind pumping. The Ekman, the coastal currents around there have a big, Ekman effect has a big role in that coastal current. And if you change that Ekman, you can change the amount of warm water that gets up to the continental shelf. And that comes from a paper by Spence et al. 2014. I'll show you a slide from that next. And I already mentioned the arrested Ekman layer adjustment. And there's another thing that's a negative feedback, and that came out in the Goddard et al. Work and the Mormon et al. Work. When you have freshening along the coast there, you can get enhanced baroclinic fronts, which in fact create more of a barrier or a negative feedback to heat transport along the shelf. Now, there's questions about whether that increased baroclinicity will in turn increase the eddy activity, the mesoscale eddy activity along the shelf. But that's, I think, still a research question. In these models that have a 10th degree resolution, which down there you get to around 3 or 4 kilometer resolution of your grid spacing, the increased baroclinicity acts as a barrier towards warming under the ice shelves. All right, so this is just a bullet point of some different theories that have been put out. Let me just talk through a few of them that I've been involved in. Well, this one I'm not involved in explicitly, but this is one of my favorites early on from Stewart and Thompson work, GRL, from I think 2013, in which they look at a process model and they look at isopycnals. And in some parts of the Antarctic slope region, you can have isopycnals that reach upward from the deep onto the shelf. And in some of those regions, you can get mesoscale eddies, which transfer heat from off the shelf up the slope and then move that heat toward the ice shelf. Not all the regions have this, this sort of connection, and there's only certain regions that you do around the continental shelf, but in those regions, there's some role for mesoscale eddies to affect the slope. This is a schematic from the Spence et al. Work in which we looked at the winds, and so the blue is the climatologically normal case, and the red is the, say, climate change case, or the poleward shift of the winds case. And so the coastal current is largely affected by Ekman pumping. So it pumps those isopycnals down and creates a border or a barrier between the warm offshore water that sits offshore from reaching the coastal shelf. If you weaken that Ekman pumping, you allow for those isotherms to bow up a little bit, and that bowing up can create an anomalous warming at the base of the ice shelves, or at least along the coast. And so here's a picture here in a global model of what that can be, what happens when that happens. You just shift the winds, and this is an anomalous temperature over the upper 1,000 meters in this model, and you get upwards of 2 degrees centigrade anomalous warming that's almost around the whole continental shelf of Antarctica. And when we first saw this, we were pretty astonished at this this feature. And it, in the end, it was pretty simple explanation, just changing the winds and changing Ekman. But it's pretty pretty dramatic change here, what the effect of the winds can have on that coastal temperature. So I mentioned earlier, and this is another mechanism that we have been thinking about related. So the figure here, this is just a time-independent sort of equilibrium result. So you change the winds, you let it equilibrate for a decade or two, and this is a change in temperature pattern. But what might happen in a transient became a question that we started to address after this study. And I'm not going to go through the upper figure. I'll keep it in the talk for those that are interested. And this is a nice schematic from Anna Wallin's paper in 2012, looking at arrested Ekman layer dynamics along the continental in the Amundsen Sea. But the gist of this is that even when you have a linear wave, say a coastal Kelvin wave that moves around the coast, you change the baroclinic pressure gradient off the coast, and that effect, when it hits the coast, can lead to what's called a baroclinic adjustment through an arrested Ekman layer dynamics, which in this particular case can move the isotherms up the slope, just like this figure here for the time mean case. But you can have this happen in a time dependent case, and that arrested Ekman layer response can be quite fast. It can be on the order of hours or days, depending on the slope and the stratification. Tau equals F over N alpha squared, where alpha is your slope, is a result that comes from the work from McCready and Rines in the early 90s. And so it's an interesting effect. When we started looking at waves going around the continental slope, we started seeing patterns of temperature, not quite as dramatic as this, but warming patterns that were stationary around the western side of Antarctica. And we started to wonder, how can a linear wave, a Kelvin wave or a coastal trapped wave, which is mostly linear, lead to something that's stationary, because the waves are moving around the coast all the time. And so what we were seeing is, and we interpreted it as an arrested Ekman layer response to change in wind patterns. And this is a pretty complicated figure that made it into our schematics of the paper. And it just summarizes what I was talking about. The lower right is the anomalous changes here. You have a change in the sea surface height, which changes the barotropic pressure, which leads to an arrested Ekman layer response, which off the west coast of Antarctic Peninsula, with the temperature isolines aligned as they are, can lead to an upslope transfer of that warm water, which can lead to melting of the ice shelves. At least that's our hypothesis. So I apologize for not going through this in detail. This is a survey talk. I could give a whole talk, at least 30 minutes or 45 minutes on this mechanism itself. So back to, now that those two studies were done with ocean force simulations. What happens in a climate model is what I show here. And you see this pattern here with a double CO2 pattern in the 10th degree climate model. And let's focus on the upper left, which is a temperature pattern. One of the things that we see is a warming in the Ross Sea. And that's something that also was shown in the Mormon et al. Study, as well as the sort of Antarctic warming along the continental shelf. The Ross Sea is not very well observed, and it's an intriguing model result, which I think prompts us to look more into the Ross Sea to see if potentially there's some hot spots for warming that might be happening there. And I mentioned earlier that the increase in the baroclinicity across the front, the lower right panel, which shows that, can increase the barriers for warming getting toward the shelf. What happens in the Ross Sea is that baroclinic front is really close to the continent. It doesn't sit that far offshore. And so it allows for that warm water offshore to penetrate or spill onto the Ross shelf. Whereas in the Weddell Sea, that front is fairly strong. And so you get a pretty good barrier, at least in this simulation, toward warming in the Weddell Sea. You don't see much of an anomaly in the Weddell Sea relative to the Ross Sea. So those that don't know your geography of the Weddell Sea, and I can't use my pointer for some reason, the Weddell Sea is WS and RS is the Ross Sea. So let's not talk about the salinity or the sea surface height. Let's move on to the next slide. So now that I've given you some studies from the old model, the CM2 model class, I'd like to close the next 10 minutes or so and look at extreme sea levels using a new model that we've developed at GFDL. This is a model we call CM4. It's only at a 1/4 degree ocean resolution, and it's got a 100-kilometer atmosphere resolution, but that compares to our previous CMIP class models, which had a 1 degree ocean and a 200-kilometer atmosphere. So the thing you get with a 100-kilometer atmosphere, at least in this particular 100-kilometer atmosphere, is you start to get a representation of tropical cyclones and stronger northeasterlies and extratropical cyclones that are really essential if you're going to ask questions about extreme sea level. And what you get with the 1/4 degree, as I've argued already, is that you start to get a reasonably good representation of the coastal shelf. And in fact, in some regions, you get coastal embayments or harbors and stuff like that. So let's ask the question, what happens in this model when you start to look at extreme sea levels? So this is a study that came out recently from Yin, Griffies, Witten, Zhao, and Zana in Journal Climate for those that are interested in more of the details. So let's look at, if I can do this. Yeah, this is a movie, an animation of sea level pressure in the contours and the sea surface height, the ZOS field. ZOS is the jargon term for sea surface height in CMIP language. And you see that you get strong extratropical cyclones off the northeast, and you get you get some representation of the tropical cyclones in the Gulf of Mexico. So the jargon here is that CM4 is our CMIP6 era GFDL model, published by Held et al. 2019. And we have a new atmosphere, a new ocean, and as again, a respectable resolution. You clearly want to have much finer resolution if you could, say even getting down to 25-kilometer atmosphere to get category 4 and 5 hurricanes. But at 100-kilometer, you start to get category 2 hurricanes, and you get a good representation of extratropical cyclones. So here is a picture from just the models. I don't have any comparison to data, and you just have to trust me that it's not a silly representation of TCs in the top with the climate control simulations and the extratropical cyclones in the bottom panels here. And we're focusing in this study on the east coast of the US and the Gulf of Mexico. So this is a nice spaghetti plot to show that you get some storms in these models. So we looked at some statistics and the standard deviation, the skewness, and the kurtosis of the sea surface height, the daily mean sea surface height. And these are kind of standard diagnostics to look at. Of course, standard deviation is just looking at the fluctuations of the patterns. The skewness is looking at how skewed the distribution is toward one side or the other. And the kurtosis highlights the extreme events. So the standard deviation, if we look at the left panel here, we see, and this is in the control simulation, we see the large values off shelf, and that is due to the mesoscale eddies that are sitting off the continental shelf. And as you get to the, roughly that black line is 1,000 meter isobath. And as you go inland of that isobath, you start to see a reduction in the variance until you get right to the coast, where you start to see some of the coastal waves that are happening in this model. The skewness, you get a positive skewness near the coast. And why is that? I'll give you a brief outline of that. Let's look at in the Gulf of Mexico, for example. Let's look at New Orleans, which is a hot spot of both the skewness and the kurtosis. As you have a tropical cyclone coming in toward the north, you have strong winds to the west of that cyclone, plus you have winds from the movement of the cyclone itself coming from south to north. So you have, what you see here is a larger positive skewness. So that means you have more high distribution on the positive side of sea surface extremes than you do on the negative side. The negative side would correspond to the offshore winds. Now the offshore winds coming from land are going to be slower than they are going toward land. And they're also going to be affected by the fact that the storm is not moving to, the storm is moving to the south, to the north. So that helps you explain the skewness, the positive skewness around the coast in the Gulf of Mexico. You have a similar argument along the east coast of the US due to the northeasters, which give you, actually give you more alongshore winds that give you Ekman drift toward the coast with the northeaster. They're called northeasters because the winds come from the northeast and you get a Ekman drift toward the coast, which gives you a sea surface rise, preferably. Now the kurtosis is, as I said earlier, a measure of the extreme sea level. And as you can see here, the main hotspot for sea level in this model is New Orleans. And it's really an unfortunate sort of perfect storm of geometry and coastal morphology that leads to this positive kurtosis of New Orleans in this particular way. And I think the people that live down there, including lots of my family that lives down there, has no pretense that they're living in a safe zone in regards to sea level and climate change. So here's a few case studies in the control simulation of what we can look at in this model here. Again, focusing on a particular event in the Gulf of Mexico. We have the dynamic sea level on the left, top left. We have an inverse, so you have an effect from storm surge in this model, or just sea level really in this model, due to two main effects. One is the winds and one is the inverse barometer. It turns out that the winds are about 80 or 90% of the rise near the coast, and the inverse barometer is another, say 10% or so. And so you see the middle panel here, we see the winds of the tropical cyclone in this simulation, and we see precipitation. One thing that I learned when I did this study, that the precip, and you sort of experience it if you live through a tropical cyclone near the coast, is it dumps a tremendous amount of water from rain onto the coast, and of course over land and flooding over land. But even on the coast, in that water, when you have a very broad continental shelf, that water takes a few days to propagate away as a barotropic wave, right? You put an undulation on a free surface and it'll propagate away, but the wave speed depends on the depth of the ocean. And when your depth of the ocean is maybe 100 meters over a broad continental shelf, that water can stay around for order a few days, which is long enough to cause coastal flooding. So the precip effect is a non-trivial contributor to sea level rise in these events, these extreme sea level rise. And of course, one of the things you get when you start to represent mesoscale eddies in these models is you get the ability of those eddies to affect the tropical cyclones. And you see the lower left corner where you see a nice Gulf Stream ring in that simulation, and that ring can affect the temperature of the sea surface, and that affects the storm itself. And the bottom right shows you the Ekman effect, the Ekman suction, which brings up the cool water from below underneath the tropical cyclone. So the purpose of these slides is just to show you that it's not a silly simulation. This model has a reasonable representation of the dynamics of tropical cyclones and their effect on the ocean and the ocean's effect on tropical cyclones. And so it leads us to study the next question. Now that we have a model that has a reasonable representation of weather events, extreme weather events, as well as reasonable representation of the coast, let's look at the extreme sea level in these simulations. Before I do that, I want to mention another thing that I learned in doing this study is the effect on storm surge and the wind effect. So if you remember your basic coupled modeling, that the wind stress has a quadratic relation to the wind speed through the bulk aerodynamic formula. And so you see these fits to the daily wind speed on the lower and the surge height in the two figures on the two panels here. And you see that quadratic relation between wind speed and surge height. And that's again related to the fact that the wind speed is, the wind stress is quadratic related to the wind speed, and the stress ultimately drives the surge. And so you see especially a big effect of that in New Orleans because it's exposed to these big storms. So under climate change in this simulation, we get, of course, thermospheric sea level rise, and you get different sea level rise on the top right panel, different cities along the coast from Halifax down to Houston, and especially off the east coast of the US, you have a big effect from the reduction of the AMOC. So reduced AMOC, and it's a long story that's been around for a decade or so, reduced AMOC in these simulations can create changes to the sea level along the east coast of the US, basically due to change in slope of the Gulf Stream region, which rises sea level along the east coast of the US. That is the dominant contributor to sea level rise in this model simulation that contributes on top of these extreme events from northeasters. Whereas in the Gulf of Mexico, you have much less connection to the AMOC, and you have more of a connection to the just tropical cyclones contributing to the extreme events there. So the patterns of sea level change that we see in this model, and this is something that if you remember the top left panel, if you remember the picture from Cesar et al., you get this warming near the coast and cooling in the open ocean here. And so you get likewise a sea level rise along the coast, top left panel, and a sea level fall right off the coast. And that's just a change in the slope of the Gulf Stream effectively. And let's skip the two right panels for time. So what happens to the extreme events? So let's just look at the distribution here. The Northeast, Southeast, and Gulf of Mexico. The Northeast is north of Cape Hatteras. The Southeast is Cape Hatteras down to Miami, and then the Gulf of Mexico. And we look at different simulations here, a 1% CO2 idealized, an abrupt 4 times CO2 event, and you get the expected shift to the right of more extreme events in these simulations. And I said it already, that the sea level rise in the extreme events along the northeast, the east coast of the US is largely dominated by the reduction of the AMOC, which increases sea level along the east coast. And that in turn allows for higher extreme sea levels because the baseline sea level itself is higher. And you can detect, at least in this model, that change in sea level even before you can detect global sea level changes, the effect due to thermospheric sea level rise. The Gulf of Mexico is much more noisy and much more prone to extreme event increases due to the increased tropical cyclone strengths, which are found in this model. So let's get some comments on this particular case study. Under most natural weather processes, the Gulf of Mexico and the East Coast is most vulnerable to storm surge and relate to sea level rise. I wish I could see. I'm gonna do an X. I can't even read my own slide because everything is covered here. Okay, can everybody see that still? If not, somebody yell. Under natural weather processes, the Gulf of Mexico coast is most vulnerable to storm surge and related daily extreme sea level. So I want to emphasize one point about this study. I'm not talking about coastal subsidence or channelization due to oil extraction or mineral extraction and subsidence. This is a climate model study that's looking only at sea level rise due to changes of storms and changes of mean sea level, background sea level. So there are lots of other things going on in New Orleans and the Gulf of Mexico that have an effect. And glacial isostatic rebound is affecting them as well. So with that caveat, we find that New Orleans is a notable hotspot. And again, look at a reminder to myself to say that it's really the geometry of that region. And there's a lot of role for the mouth of the Mississippi. And of course, on top of everything I'm talking about here, mineral extraction and channelization, which has contributed to the erosion of that coast. So that many predictions are New Orleans will be a coastal city in the next few decades, which will be really difficult for them. The time of emergence, which is some results I did not show, is a term that refers to when you can start to detect changes in these simulations. And the anthropogenic effects of sea level, extreme sea level rise start to emerge in these simulations about 20 years along the east coast of the US, largely as a function of the slowdown of the AMOC in these simulations. So what's in the future, at least at GFDL? We're moving toward an even finer resolution ocean and a finer resolution atmosphere. We have this hierarchy here. We actually have a ½ degree ocean and a ¼ degree ocean hierarchy, and we're moving toward, in the next few months, an 1/8 degree ocean coupled to a 50-kilometer atmosphere. So as I mentioned earlier, extreme event study really requires strong weather patterns, realistic weather patterns, and the 50-kilometer atmosphere will get us even better representation of these tropical cyclones and extratropical cyclones. So we're kind of excited about that, as well as the better representation of the coast to get at even more fine scale representation of these extreme processes. So let me just give you some closing comments. And I apologize for going so fast, but hopefully I gave you a gist of some of these studies that you can look at further if you're interested. I'm very much interested in ocean fluid mechanics and how it can be more important for climate. And in particular, as we get to finer resolutions, fluid mechanical processes, eddies, coastal waves, the effect of tropical cyclones, extratropical cyclones, precipitation patterns, melt patterns, all of that has a role in asking questions about sea level near the coast. And the ocean ice shelf interaction problem is a particularly challenging problem because of all of the processes going on in the Southern Ocean. But it's a rich problem, and I think there's many careers, many decades of a career to be made out of study and processes around the coast, especially around Antarctica. I argue that fine resolution, even finer than the first baroclinic porosity radius, is necessary in some places to faithfully represent a lot of these key processes. We can aim for parameterizations, and I've done my share of that, and I'm working with the climate process team to further parameterizations of mesoscale eddies. But I still think there are certain processes that are just too difficult to represent through parameterizations that you need to, if you're going to ask these questions, you need to bite the bullet and enhance the resolution to do a robust study of those processes. We also need fine atmospheric resolution to get these strong weather events. But I want to emphasize also that fine resolution is not a magic bullet. We still need to put some emphasis on better numerics and better closures even when we go to fine resolution. And one of the cutting edge questions for the GFD people out there is the eddies and the flow and the waves and how they interact with topography. I think it's an age-old question of GFD, but it continues to be a question that's starting to be more high profile as we get models that start to do a better job of that representation. It's not just the shallow water or the QG models that you can use to study those processes. You can do realistic modeling now and look at how waves and eddies interact with topography and how they affect sea level near the coast. Those are really interesting problems. So another picture from the Southern Ocean as I thank you for sitting through this webinar, and I apologize for going a few minutes late. Thank you.
Thank you very much, Stephen. Do we have any questions from the audience?
I think there's something in the chat.
Ah, let me just have a look at this. So there's a question from Philip Orton.
All right, I can't see it.
Philip, if you're willing, it'd be nice to.
Can you hear me?
Yeah.
Wonderful.
I was going to say, I believe I've seen sufficient evidence by now that the effect of the AMOC flowing on New York Bight and Mid-Atlantic Bight sea level is model dependent. I'm not sure I have the references handy to prove that to you, but and that they can change with higher resolution. So do you have evidence that your model's resolving that effect? I know to some extent this is just, you know, using the latest model, and you're, you know, do you have good evidence that you're resolving that effect well enough and that you have an accurate result with this model for the AMOC driven MSL rise in New York and Mid-Atlantic Bight?
Yeah, it's a good question. You know, evidence is in the eye of the beholder partly, and also the data. I'm going to waffle on that answer. I don't know, to be frank. I'm not aware of what study you're talking about to show some model dependence. There's not a lot of models that are run for climate change at a 5-kilometer ocean resolution or 10-kilometer ocean resolution like this one. In fact, I know of 2 on the planet that have run at this resolution. If you're thinking about regional models, in my opinion, have their limitations based on the boundary conditions you apply at the region boundaries. Regional models of the North Atlantic in particular have strong dependence on the northern boundary. You can get a good Gulf Stream separation or not, depending on what you'd put at the north, the overflow regions in the Denmark Strait in particular. So does that answer your question? Or if you can provide more details about what you mean by model dependent, what models are you talking about is maybe what I'd have to ask.
Yeah, I don't remember if it was higher resolution regional models or if it was coarser global models. So I think it was at the AMS conference this winter, but yeah, you know, maybe I'll send you an email, but I guess it's always a good question is, when do you know if you have good enough resolution?
That's a question that has been part of my career, and I don't think I'll probably retire before that's answered sufficiently, at least in my regards. I mean, one of the things that we tried to do is at least evaluate the integrity of the control simulation in this model, and at least in regards to the water masses, it's not perfect, but it is better as you go to finer resolution in this model. And the model has its problems. The Gulf Stream in this model is not very good. But the argument we made in this particular paper is that the coastal processes and the coastal representation is pretty darn good. And it's definitely better than the 1 degree. And so if anything, this is a provocative result. It's not necessarily a prediction. It's a projection, and it's something that is meant to provoke the community. And it's definitely provoked the fisheries community because of the finer resolution and the bigger signal that we're seeing in this particular realization. And it's argued that you're seeing a huge signal in the Gulf of Maine in the real world, in the fisheries world, which the 1 degree models don't capture at all. Yeah.
Okay, we have another question from Natasha, and then I see Gavin's got his hand up. Natasha, would you like to unmute? Yes. Wonderful.
Hi everyone. Hi Stephen. Thank you. That was a great talk. So my question is about the arrested bottom boundary layer turbulence, and that because it brings me back to hundreds of years before when I did my PhD thesis on that. I know that a very critical element of that is the vertical resolution, because we are talking about coastal regions, the shelf essentially, and the current rubbing against the boundary. So now variations in that interior current have to be vertically resolved, particularly as we go closer to the boundary. And that would have to mean that the vertical resolution is very much finer than what current models have. So when you are discussing increasing horizontal resolution, do you also accompany that with vertical resolution changes?
Yeah, great question. I'm part of a paper that came out in 2017 by Stewart et al., in which we talk about the needs of vertical resolution in these simulations. It was less related to the arrested Ekman layer, but more related to just representing vertical baroclinic modes. And as you know, as you go to finer horizontal resolution, you start to admit more and more baroclinic modes, but those modes have a vertical structure. And if you want to represent them globally, everywhere around the planet, you have to enhance your vertical resolution. The simulations that we looked at this particular phenomena with, I believe, was 75 layers, 75 levels, which is a reasonably high resolution, especially in the upper ocean, where most of these this arrested dynamics was happening in the upper few hundred meters. So I can't say that we're explicitly resolving everything, but it's not. It's a respectable resolution. But again, yeah, I should have emphasized a very good point that the push to go to finer resolution it should be coupled between the horizontal and vertical. And in fact, I know that a lot of people looking at submesoscale processes look at like 200 vertical layers because they need to get those strong vertical motions resolved in their simulations that the submesoscale captures. And I think that you need that vertical resolution to get better representation of eddy topography and coastal current topography interaction as well. There's no free lunch. You need to bite the bullet and do some resolution if you want to start to resolve these processes better.
Yep. Thanks.
Hey, Steve, Gavin here. As Craig was talking to you a little bit before the talk, one of the things that we're kind of interested in is the coupling between the Antarctic ice sheet and ice shelf melt and the circulation anomalies. And when you're kind of like thinking about how to include more and more processes, you want to be putting in the things that are going to have the biggest impact kind of progressively, and then you put in the things that have smaller impacts, right? And one of the things that it strikes me with the current CMIP6 crop of models is that none of the ones that have been put into the archive so far, including ours, have a representation of the freshwater impact in the Southern Ocean. And the work that Craig has done, and the work that Golledge has done, and has been like 2 or 3 papers, seems to indicate that is it's not just a minor thing. It actually changes the sign of the response in the Southern Ocean, and has a very complicated impact on both the stratification and the sea level height, sea surface height there. So, I mean, the case you're making for the importance of resolution is, I think, is very clear. But should we not be also worried about this? I mean, like, there's a lot of models, including the GFDL model, that have very large warming in the Southern Ocean in their projections, and excessive warming compared to the observations so far. And even if they had a higher resolution, that still might be, more detailed, but more wrong compared to models that might be less well resolved, but do have, one of these, this kind of major missing component. Any random thoughts on that issue?
Well, I couldn't agree with you more. As you may recall, I was part of the Bronselier et al. Paper that came out 2 years ago, which did the freshening in the ESM2M older version of GFDL climate model, and showed a huge effect even of the intertropical convergence zone and the sea ice as well. I guess in defense of CMIP6, which, I mean, you know as well as I do, we just didn't have these scenarios in mind when CMIP6 was defined, whereas there's a project that Joellen Russell's been promoting through FAFMIP, which I'm part of, called SOMIP, which is got one of the scenarios is a melt scenario, just to look at how the models respond under these very simple melt scenario. I agree with you that it would be nice to have those melt scenarios in even before we have ice sheet models or ice shelf models, because the ice shelf coupling problem is a difficult problem, and a lot of us have been waiting for that. Whereas I think, you know, Ben came along with Mike Winton and myself and just said, hey, let's just see what the ocean and the couple model does when you put fresh water onto the coast. And yeah, there's been other people that have done similar works in ocean forced models. One of the counterpoints that I want to raise, and it's a paper that is still under review, but I'm hoping it's close to being published, is a study we did in the 10th degree model, the CM2.6 model, in which we didn't put in a melt scenario, but we looked at polynyas in the model and in a climate change simulation, an idealized CO2 rise simulation. The polynyas, as you may recall in a paper by De La Verne et al. In the CMIP5 models, polynyas start to stop in the Weddell Sea in the simulations around in the Southern Ocean in the early 21st century. Whereas in our high resolution model, it doesn't stop. We get another polynya. And the argument we make is that when you have a better representation of the coastal current, that meltwater stays in the coastal current. It doesn't go out into the open ocean. So it has a big role to play in whether you get open ocean convection or not, whether you have the coastal current resolved or not. So that's a bit of a, you know, come back to your statement that we need to get these melt scenarios in there. I agree with that, but the response of the model to the melt could be very dependent on whether you resolve the coastal current around Antarctica or not. That's the sort of conclusion that we made in this study, which again is still under review. It's close to publication, but it's with Carolina DeFore and her student Joe Lockwood and at McGill. So you might want to look for that. Yeah, so in summary, yes, I agree. Melt events are really exciting science and highly relevant societally, and we need to be doing those more and more with our models to really bang them hard to see what they're going to do.
Yeah, thanks.
I like your beard, Gavin. Is that a COVID beard? Or has that been around more than the COVID?
No. It's yeah, no, it's a quarantine beard. So I haven't shaved since we started working at home, and I'm just gonna let it go until we get to the end. So
very good.
2 more questions in the chat box.
Yeah, thanks. So Max, I think you're next. Would you like to unmute?
Sure. If
Thank
you can't see the question, I was just wondering about whether you see a need to start explicitly including tides as the resolution increases for the questions you've been discussing today.
It's a good question. There's some nice work that Andrew Stewart has done at UCLA with tides and a very fine resolution MIT GCM simulation of at 148th degree, and he's looked at tides around Antarctica. In general, tides can play a role, and I would say it's still debatable. And I'm doing some work with the Australians and putting tides in this 10th degree model, and then the questions are, does it affect the heat transport across the continental shelf around Antarctica? I'm looking more in the Antarctic region in these studies. It's still an open question in my mind. I think probably yes, but I don't really know yet. I mean, naively, tides just things slosh back and forth and it's kind of linear. But when you have warmth coming toward a shelf and you have a nonlinear melt event, that breaks that linear assumption. And you also get rectified effects that create stronger currents in some places and weaker currents in other places. So I think we're going into the world when you start to get models that get to the 10th degree resolution or maybe even quarter degree resolution, that tides may start to be something sensible to put in. It definitely makes it more difficult to analyze these models. You got to de-tide all your output. but we might start to get used to that problem because it could play a role. So it's kind of a wishy-washy answer, I acknowledge, but I am doing some work on looking at tides through collaborations because we have some hypotheses that it might play a role. I don't have any definitive answers to that yet, however. Thanks.
Thank you.
We have another question in the chat from Nikita's. Would you like to unmute?
Sure. Sure, thank you. But I think that Steven actually answered my question because it was Gavin's questions as well. My comment was about the cryosphere's interactions and how can we, in fact, capture them. What is the timeline you think? Maybe that's a good question for everyone. What's the timeline you think about getting something useful there? 5 years, 10 years, 30 years? What do you think?
Yeah, so I mean, at GFDL, this is a hat that I'm partly playing, but more in connection with Bob Hallberg and Olga Sergienko. Olga's an ice shelf person, and Bob is an ocean modeler. So with our new models, namely MOM6, it's a vertical Lagrangian coordinate model, and it allows for wetting and drying to be naturally represented, and so you can allow for the grounding line to move backward and forward every time step without readjusting your land sea boundaries. And that provides, at least from the ocean ice numerics, a pretty nice piece of a tool that you can use to look at the moving grounding line question. And we have that in our models, not in our CMIP models, but it is in the models, and what we really need is a champion to start making use of that. We had a postdoc a few years ago named Dan Goldberg who moved on that did some early process studies looking at moving ice shelves and the currents under the ice shelves. I believe he's at MIT now, I'm not sure. Or no, maybe he's in the UK. It's a tough problem numerically, and I know that the Los Alamos group is doing their own approach, and NCAR and it sounds like GIS is doing their own approach. And definitely groups in the European. So I would guess, when you say the timeline, it depends on when you can start to trust the simulations, at least trust them numerically. It's probably a few years, but it's not as far out as it used to be. And we've made a good bit of progress from the numerical side in the last decade, I'd say. And you do get a lot more people out there. I mean, the education of smart, energetic postdocs is happening. I mean, we're getting people moving in from allied fields like solid mechanics and engineering. We're trying to hire somebody at Princeton who's got an engineering degree that's looking at these problems. So I'm encouraged from the progress in that regards. In regards to the CMIP, when we're gonna get this into CMIP, hopefully by CMIP 7, but it's gonna be many iterations on the problem before we start to all have a consensus. I think it's at least a decade before we really get to some strong consensus on what the models are telling us and if we really trust the models.
Thank you.
Sorry to put you on the spot. I noticed a moment ago that Olga had her hand up. I was just wondering if she was still interested in asking a question.
Well, yeah.
Thank you. Thank you, Olga. Go ahead, Nancy.
Actually, a reason I had was just to echo you in terms of answering a question that Gavin had about resolution. So these things are not mutually exclusive. And a question about freshwater adding to the Southern Ocean versus the resolution. I would say it would be a bit dangerous. It might be not exactly the right word, but start with freshwater inputs to the Southern Ocean without having at least necessary resolution. I cannot tell you what that necessary resolution is, but definitely not 1 degree. So, and I think Ruth's talk gave exactly right illustration why that could be the case. So in that regard, what Steve presented here today in terms of the resolution has to be increased before something can emerge. And from my glaciological or ice sheet person or whatever freshwater question, I would rather see the increased resolution first before a question about the effects of freshwater or the effects of the discharge of ice into the Southern Ocean should be looked at least seriously. So that was the reason for my hand being raised. And answering to the latest comment, I agree with Steve again that it's much closer in terms of having interactive ice sheets and climate models right now than it was before. But there are a lot of unanswered problems in terms of glaciology and ice sheet dynamics itself. So it might be, some aspects might be premature, even considering putting in climate models or system models, because the whole thing might be diverged and divert to the wrong direction. So there is a caution in that aspect as well.
Can I respond to that very briefly?
Yeah, go ahead.
I mean, Steve, and you have made good cases for what extra resolution gets you, and I think that those things are important. But if your CMIT model is now running at 1 degree and you want it to go to 1/10 of a degree, it's a factor of 10 in 2 directions plus times. It's like a factor of 1,000 more computation to do that, right? So that's a big ask, and it's not that we're avoiding it because we're scared or something like that. To do that kind of thing means that we don't do a lot of other things, and in fact we can't do many other things. Whereas putting in a new parameterization or a new connection between ice and ocean or between freshwater and things, they're relatively cheap. It doesn't cost you anything more to run a model with that.
I would be quite careful in terms of, yes, it is cheap to put a parameterization, but then does it make any sense, the parameterization itself? Because
the test of whether something makes sense is not an aesthetic choice. It's whether the models that we have right now are representing the changes that we're seeing right now that we can calibrate the models against appropriately. And one of the things that Craig showed in his paper that just came out is that if you look at the trends in the CMIT models around the Southern Ocean, they are uniformly outside of the range of what the observations have shown, right? So there's something that they're all doing wrong that is having a order 1 effect on the trend, right?
But
so
how do you know it's fresh water from Antarctica?
Well, that's what we're testing. I mean, Craig's paper tests that, and it seems to suggest that it's the right order of magnitude to produce that result.
In counter comment on your comment, the very brief one, I'm not saying it should be 1/10, although obviously I would very much prefer that. However, there is a limit. So in examples that Steve showed with 1/4 of a degree, it's again, probably not enough, but in terms of the resolution. So it does not have to be like extremely high, but nevertheless, it should be higher than what
I'm not arguing with you. I mean, I think it should be higher, but as Steve mentioned, there is a real reason why we've kind of got to 1 degree and we're waiting to jump to 1/10 of a degree, right? There are particular issues with how you do the eddies at 1/4 degree that make it suboptimal in some respects, right?
No,
do you want to jump in?
Yeah. Oh, it's no disagreement in this question. That's absolutely true. Nevertheless, there is a resolution in terms of if you add fresh water, you might get up kind of even the sign of the effectron. That's what I'm trying to say.
Ruth, sorry to pick on you. Ruth looks like she wants to say something. Is that true?
Yeah, I just wanted to, I guess, to give my 2 cents, given that I've did the high resolution study side of this, and I definitely don't think there's no use of having freshwater perturbations on low resolution models. I just think that you need to be asking relevant questions with them. So asking climactic scale questions with a low resolution model and putting freshwater perturbations on it, I think that's relevant. Looking at feedbacks to the ice shelf melt, probably not relevant. It's just, I think it just depends on your question and you have to be careful. I think I've seen a lot of people trying to answer questions of how does the ice sheet respond with a low resolution model? And I don't think that's necessarily appropriate, but that's not to say that, but I also, the kinds of high resolution models that I were working with those, it's not appropriate to then look at the, you know, the shift of the TMZ, for example. I mean, our models weren't even coupled. So, you know, there's different couples for different problems, is my peacemaking comment to that.
Yeah, in regards to the no man's land of the quarter degree, I mean, I do believe that there are some problems with the mesoscale parameterizations at that sort of intermediate regime, but I was always trying to make the case that you do better with the topography, and you do allow for certain shelf processes more faithfully, at least around North Atlantic and the Gulf of Mexico. So as Ruth said, I mean, it depends on the science question you're asking. And yeah. I also think that it's useful to be provocative. The coarse resolution models are incredibly provocative because you can do so many interesting experiments with them and sort of guide or give motivation to the more process studiers to focus on things and figure out the processes. That's kind of how we do that. That's how we do our modeling. And I think to say we can't do something because we're not resolving it, that's important to acknowledge, but then you say, well, is there something else that's sort of going around it and asking another slightly different question that gets at the first question, maybe in a different way, or has some role in provoking the first question. All right, is that it? Thank you.
Do we have any further questions, comments? Nope. Okay, so we're about 20 minutes over, so I'll just say a big thank you again to Stephen and for everyone for joining us today. I hope you have a great rest of the day.
All right, take care.
Bye-bye.
Thanks, guys.
Bye-bye.
Thank you.
Thanks, Steve. That was great. Good to see you.
Thanks, Gavin. Yeah, good to see you.